All right. So we ended last time, let's move this just a little bit. We ended last time talking about combustion reactions, and I told you that if it's a carbon-containing compound, like most of the fuels that we burn for combustion, like natural gas or gasoline or coal and all kinds of other things like that are sometimes they're called fossil fuels, but those are usually carbon and hydrogen containing compounds that will produce CO2 and H2O when they combust. Let me add something here. This is usually called complete combustion. I guess I wrote it right there, but so complete combustion of a carbon-containing compound is fully turned into CO2 and H2O. That just means there's sufficient oxygen, there's enough O2 around to make CO2. What would be a more harmful product that could be formed if there wasn't enough oxygen to make CO2? Carbon monoxide, CO, comes from incomplete combustion, and if there's even less, it can just make C. So here, let's just write over here, incomplete. Combustion can make carbon monoxide or just carbon. So carbon as a product of a combustion reaction is smoke. So anytime you see a fire that's given off smoke, that's just the carbon that's being given off. So anytime there's smoke, there's probably carbon monoxide too. That's why you cannot build a campfire in your living room. For instance, the carbon monoxide is poisonous to you. Okay? But you really only need to worry about complete combustion. The only other thing I want to tell you is that if there's a compound that has some other elements to that, the product here instead of carbon dioxide would be the oxide of that substance. So an S-containing compound, for instance, would make sulfur dioxide as a product, okay, instead of CO2. So be aware of that. But that should make some sense, because if this has carbon and hydrogen in it, the carbon of that became CO2, the hydrogen of that became H2O, it became water. Okay? So I only think I have to tell you this because one of the mastering chemistry questions, I think, has combustion of a sulfur compound. So just be aware that the sulfur turns into SO2. Okay? In the next chapter, when we calculate amounts in reactions, we're actually going to calculate how much CO2 is produced when we burn a hydrocarbon fuel like that. Okay? So we'll come back to that in quite a bit. But yeah, Bunsen burner there. Methane is the gas that comes out of the thing you plug the Bunsen burner into in lab. So, anybody have questions about combustion? You should be able to write and balance a chemical equation for the combustion of some given compound. Okay? But all it is just your given compound. The other reactant is always O2. If it's a carbon-containing compound, CO2 and H2O are the products. And then it just needs to be balanced. Okay? All right, let's talk decomposition. Decomposition is actually pretty easy to spot because all you have to do is count the reactants and products. Okay? It is one reactant that decomposes. It sort of breaks apart into two or more, into multiple products. So it's just something sort of breaking apart, one thing forming multiple products, and we call that decomposition. So there is a example here of H2O2, which undergoes decomposition. Who knows what H2O2 is? It's not water. It's hydrogen peroxide. Okay? It's sold in drugstores in those brown bottles, right? So hydrogen peroxide undergoes decomposition. Let's leave room for coefficients to make H2O liquid and O2 gas. So Then I think we just need to balance. Probably need a 2 here and a 2 there. Okay. But this reaction is slow on its own. But it happens. This reaction right here is the reason hydrogen peroxide bottles have an expiration date on them. It's usually a couple of years or so. But after a couple of years, on its own, hydrogen peroxide will decompose just into water and oxygen gas. So if it's a brand new bottle, but it's been sitting there for 2 years, when you open it up, you'll probably hear and feel the oxygen coming out of it, but then it'll just be water in the rest of the bottle. Okay? And those bottles are brown because light actually speeds up that decomposition reaction. So if it's in the dark, it lasts longer. So slow on its own, not terribly interesting. A catalyst, though, is something that will speed up a reaction but is not consumed by the reaction. So if we added a catalyst to this decomposition, this reaction could happen fast. Okay? But typically, you only need a little bit of a catalyst because it's not something that's used up. So the way we'll write this, we'll write the same reactants and products. Okay? We'll write 2H2O2 making 2H2O and just one O2. But this time, I'm going to write Ki up there as a catalyst. Potassium iodide is a common catalyst for this. And we write the formula of a catalyst up above the arrow because it's not really a reactant. It's not something that gets used up in a reaction. And it's not something that's formed. It's just something that we put there that helps the reaction go faster. So Ki is the catalyst. So that will make the difference between this taking years on its own and being done in just a matter of seconds. We see catalysts often with decomposition reactions because that's what can make a decomposition reaction useful. If a decomposition reaction was fast on its own, then you wouldn't be able to do anything. As soon as you have it, it would just decompose. Okay? So if it's a reaction that decomposes slowly on its own that you can catalyze, that makes it useful. This is a useful reaction in making oxygen gas. You did this actual reaction in the gas lab. You started with hydrogen peroxide in the test tube. You put a little bit of Ki in there, and then you jiggled it so it went down, and that made the oxygen gas as one of your products. Okay? So pretty much just recognize one reactant, multiple products, and the impact that a catalyst can make. Okay? All right, single displacement. We already talked last time about double displacement. Let me bring that up. Double displacement was when we had two ionic compounds, right? Plus, minus, and they swapped partners to make the other two combinations, right? That's double displacement because we've got two things that are swapping their partners. Single displacement, we have just one element that's replacing another. And it's easy to identify because it will be like this one. It will be an element and a compound reacting. And for the products, we'll get a different element, and EL element, and a different compound. So you can see here we had aluminum and iron oxide, but that aluminum just swapped places with the iron, and we got just iron and aluminum oxide, okay, as a product. Check out the phase labels on this one. What is that? L? Liquid? What has to happen for this reaction to produce liquid iron? Yeah, this reaction has to heat way up. This is a picture of this reaction. It's called the thermite reaction. I wish this is one I could demonstrate for you in here, but as you can see from the picture, it gets hot enough to produce liquid iron, so that means it's spraying out sparks and smoke and everything. We can do it in fume hoods. If I ever remember, I might show it to you when we're in lab sometime, because you can do it in a fume hood, but you can't do it in here. But this is the liquid molten iron. This is a ceramic container, and you usually catch it in sand or something like that. But liquid molten iron is a product of that. Okay? But it is a single displacement because the aluminum just replaced the iron. Okay? We talked about this reaction before. I think I showed you the video of those big barrels of sodium tumbling into the lake, right? When sodium reacts with water, again, here's an element and a compound. We get compound and hydrogen as an element. Okay? This is the reaction of sodium or any other alkali metal with water. They'll produce the metal hydroxide and hydrogen, which itself is flammable. Off to the side here, hydrogen reacts with oxygen to make, so probably got to be two H2s. Okay. That is a combustion reaction. So that's what happens with this hydrogen because it gets hot also. So if we do this large enough scale and it gets hot, we produce hydrogen as a product, and then that hydrogen will explode or burn or combust. Okay? So that's what the big explosions were. Okay? It was the hydrogen reacting with oxygen to make water. Hydrogen is actually an outstanding fuel source. For the amount of mass that you have, it actually gives off more heat than a corresponding hydrocarbon fuel. That's a calculation that can be done. And wouldn't it be great if our cars could be powered by hydrogen because the only waste product would be water? We wouldn't have any of this carbon dioxide, climate change, pesky stuff to be dealing with. Our car would just be giving off water as an exhaust. But, of course, the problem is storage and transportation. Much more convenient to have a liquid fuel at the gas station than a gaseous fuel. That would be than an explosive gas that you're pumping into your car, but maybe they'll figure that out. With single displacement, pretty much I just want you to be able to identify what's happening here, okay? That it's a single displacement reaction. The products are difficult to predict. Okay? For instance, in this one, we probably wouldn't have known that those were the two products that are formed without actually doing the reaction. So you'll probably just be given a reaction that you'll have to classify as one of these types for this. Okay? And then the last one I want to talk about is synthesis. It's the opposite of decomposition, where we've got multiple things that are combining together to make one product. Okay? Two or more reactants form one product, where decomposition was one thing that was breaking apart into multiple products. Right? So just sort of the opposite. These ones we can write. So let's try it. Let's write the synthesis reaction that silver and oxygen will undergo. Okay? So coefficient, what is silver? You guys know that, right? All right. So silver, pure metals are what phase? Yeah, they're all solids except for mercury, which is a liquid. Okay, so pure silver, solid. Okay, and then oxygen. But when oxygen is an element, it's not just O, it's O2 because it's diatomic, and that's a gas that you breathe, right? All right, so solid silver, O2 gas. To form the product, it's going to be a compound made out of a metal and a non-metal. What kind of compound is that? It's an ionic compound, so we need to know the what of silver and oxygen to write that compound's formula. We need to know the charges. Okay? Use the charges to write the product formula. Elements on their own have no charge. So this has no charge, that has no charge. Elements on their own are neutral. But within a compound, we use their charges to get that formula right. Okay? So silver, it's a transition metal, but it has a fixed charge. Remember what it is? Yeah, single plus, silver plus, O2 minus. Okay? So the product we'll write over here will be Ag. What? Yep, you have to switch the charges. We're going to need two of these to cancel out one of those. So Ag2O. It's an ionic compound. We don't have to worry about solubility because there's no water here. What are pure ionic compounds? Think of like table salt and things like that. What phase? Yeah. Pure ionic compounds are solid if there's nothing around to dissolve them or whatever. Okay. Then let's balance. Okay, so I've got some balancing practice by now. What do I need to do to balance this one? This one's not so bad. 2 in front of what? 2 in front of silver? I need 2 over here. If I did 2 in front of silver, then I still just have 1 O to these 2 O's over here. I need 4 silvers and 2 of those. Then we're good. Okay? Any idea why I included a picture of those fancy silver champagne glasses? One of them looks shiny and lovely. The other one looks black and disgusting. Take a look at our equation there. What do you suppose happens to silver over time when it's left out? What's that called, by the way, with silver? Anybody know? Yeah, that's tarnish. Okay? When silver reacts with oxygen in the air, it forms silver oxide. For silver, that's called tarnishing. In a more general sense, that's just called oxidation. Okay? When an element reacts with oxygen. Okay? So, yeah, that's tarnish. This is clean silver. Silver oxide is black. So that's what's formed on the surface of this one, a coating of silver oxide that can be wiped off. Or there are products that reverse this reaction or dissolve the oxide coating. But it's something that's always going to happen as long as there's oxygen around for the silver to react with. All right. Actually, here, back up on, well, here, we got room down here. I'm going to give you these words. We're not going to do much with them in this class, but oxidation and reduction, if you take a biology class, you're going to be talking a lot about oxidation and reduction. We get into those a whole lot more in the general chemistry classes. Okay? We don't really do a whole lot with them in here. But it's when electrons are transferred. We're going to talk all about electrons sort of in a couple of chapters. But there has to be a transfer of electrons, right? Because we went from neutral silver to silver plus. Okay? That had to have lost 1 electron. That is an oxidation. Okay? And then neutral O going to O2 minus, here we had to actually gain 2 electrons, but when it balances out, it works. Okay? Gaining electrons is called reduction. So oxidation and reduction happen together. That's the real reason we say the silver was oxidized, okay? Because it lost electrons. It went from neutral to plus charge. Okay? When something reacts with oxygen, this substance has been oxidized. That's where the name sort of came from. Okay? So have just a general awareness of that, especially because that'll come up probably in your future at some point, but we won't deal with it too much in here. The only other thing we'll do here in this chapter is review and make a little cheat sheet for our types, for the different reaction types that we talked about, and we'll do that in a sort of symbolic way. Double displacement was 2 ionic reactants. So what I'm going to write here is AB plus CD. Okay? And we're going to pretend those are the positive and negative ions in 2 ionic reactants combining with each other. Okay? So what would one of the products be? One of the products will start with A. It would be what? AD, because it has to be plus minus pairs, right? So AD will be one of them, and then what will the other one be? Okay. You should, and in lab next week, we'll get practice writing and balancing these. Okay? You're going to need to do it in your mastering chemistry. Okay, and we practiced that in class last time, but in lab next week you'll get even more practice doing that. But you need to be able to predict these products. And I'm going to do PDTS for products there. Okay. Use the charges to get those formulas right. Ignore numbers or whatever that were over in here. Those came from these charge pairs. Okay. Use the correct charges to get the formulas right over there. Okay. Double displacement is just this product of switching ions. It's called a precipitation. If one of the products is what phase label? Yep, if we make a solid product, then we call it a precipitation reaction. But if everything is AQ, if everything just remains dissolved, what did we actually call that? We called it no reaction. So follow the instructions very carefully in mastering chemistry when you're doing these. Okay? If it tells you to write a chemical equation, okay, it may just give you the reactants, but your answer needs to be the complete chemical equation with reactants and products balanced with phase labels. But on some of them, it says if there's no reaction, your only answer will be no reaction. Okay? You just type in no reaction in that case. So follow those instructions very carefully. Don't get points left off for just the way that you're entering it. So listen and read it very carefully for what it says, how it tells you to enter those answers. Okay? So double displacement, we can predict products, write and balance equations. Combustion would be something like where we have I'm going to do CXHY. Just a certain number of carbons, certain number of hydrogens. That's just a carbon-hydrogen containing compound, a hydrocarbon. Okay. And what's the other reactant always in combustion? Oxygen, O2. And the products of complete combustion, what does that C turn into? Yeah. The carbon, it gets oxidized, a lot like that silver did. Okay, so carbon dioxide is a product. And then we end up with, what does the H turn into? Water. But it's H2O gas because it's produced in the flame. So, write and balance for a given reactant. So I would have to give you the formula of the hydrocarbon that we're reacting. But if that was C4H10 or something like that, you should be able to write O2, write the products, and then you just need to worry about balancing it. Okay? Half of the time on those combustion reactions, you'll have an odd number of O's over on the right. So you just need to double everything so that you have an even number. We had an example of that last time. So you have to do that about half of the time. All right. The simplest decomposition I could imagine would be like AB becoming A plus B. But it's not always going to be that simple. Right? Sometimes the starting formula will be complicated and it'll split into weird parts and stuff like that. But it's just sort of number of reactant and number of products. One thing making multiple things as a result. Okay? An example single displacement might be something like this, because here's an element and a compound. And if B was our new element, what would the other compound be? It would be AC. Okay? But just being able to recognize single displacement, recognize the difference between single and double displacement, for instance, would be helpful. The simplest synthesis there is would be just like A plus B making one compound. Okay? This you can write a balanced chemical equation you can totally predict this if it is a fixed charge metal. We were able to do it with silver and oxygen to make silver oxide because there is only one silver oxide. Silver only makes a plus charge. Okay? Other transition metals like iron make multiple charges. So there's iron 2 oxide and iron 3 oxide, and they form under different conditions, and sometimes there's a mixture of them, so we can't really predict that. But if it's a single fixed charge that the metal makes, then it only makes one oxide, and we can predict that, for instance. Okay? So, but again, it doesn't have to be with oxygen. It can be really any two elements that are combining. Okay? If it's a metal and a non-metal, though, we should be able to write the product that's formed by them if it's a fixed charge metal. Okay? For all of these, you need to be able to identify reaction type from a given equation. So if you're given an equation, or if you're given the word description of an equation, to be able to write and balance, just like you did in lab this week. But then also be able to identify the type of reaction based on what it is, how it is that the atoms are grouping themselves together. Okay? That's about all we need to worry about for that. So, anybody have any questions there? Does that work? Alrighty. Well, let's move on to chapter 8.